Hey everybody! Today we are going to talk all about vectors. Now, about half, probably even more, of everything we cover in physics from here on out is going to be vector related. So you need to get really, really comfortable with these before we can even move on. So this is a fairly important video, and one you might want to come back to if you start to forget how to do it in the future. So what we're going to talk about are differences between vectors and scalars. First and foremost, what is a vector and what is a scalar, how to break a vector into its x and y components, and how do you add various vectors together. Now, before we dive straight into vectors, let's take a little trip back to middle school math, where you were graphing. Here's a little bit of graph paper that I've just projected up onto the board, and let's say we've got an x and y axis. And if your teacher would put a point somewhere on this graph, you could identify where that point is by counting the horizontal boxes, or grid lines, or horizontal distance in general. So in this case I've placed it 1, 2, 3, 4 horizontal boxes to the right, and 1, 2, 3 vertical boxes up. And I could identify the point as x comma y. In this case it would be 4 comma 3. And then you got the problem right and everyone was happy, and then you moved on. What you didn't realize you were doing was actually finding the x and y components of a vector. Now imagine if instead there was a line that went directly from the origin, the 0, 0 mark, and pointed straight up to the point that you had already identified as 4 comma 3. Now this line would have a certain length to it as well. It's traveling both up and to the right, but it has a length of 5, and I'll show you how I know it has a length of 5 in just a second. I could identify this point not as 4 comma 3, but instead as 5 with some angle above the positive x-axis, or some angle counterclockwise from the positive x-axis. And those would be the only two pieces I need. If I know it's 5 away from the origin and a certain angle theta up from the x-axis, I can identify this vector as well. So, I just referred to this thing as a vector. Now, what is a vector? Basically, a vector is just anything that has magnitude and direction. What I mean by magnitude is the length of the vector. That's going to be a positive number every time, because I can't have a negative pointing arrow. That doesn't really make sense. So magnitude is just a numerical value. Done. The direction, generally given by an angle, or could be given by the x and y components when looked at together. Now I just said that you can't have a negative value, and that's not entirely true. If I've got a vector pointing up and to the right, like I did on my graph paper just there, I could flip it by throwing a negative out front. All that a negative in front of a vector does is change its direction by 180 degrees. And that is it. So if you see a negative vector, that just means a vector in the exact opposite direction. Meanwhile, the term scalar is just a magnitude. So some things in physics just don't have a direction. For example, mass. Mass, if I have 72 kilograms of mass, I don't have 72 kilograms of mass up, down, left, right, up and to the left, or anything like that. I just have 72 kilograms. So that's a scalar. Basically, scalars are just magnitude only, and we're done. Now, back when I was on the graph paper, I mentioned how I would tell you I knew the length was 5. And that comes from knowing a little bit about right triangles. So looking back at that graph, I have a vector with magnitude 5 pointing away from the origin at some angle theta above the x-axis. I know my x component is 3. I know my y component is 4. So, if I actually fill that in, I'm going to draw a green arrow from the origin just 4 to the right, and then I'm going to draw a red arrow for the y-axis 3 up, and it will complete essentially a right triangle. And there it is. So I have a right triangle with a horizontal base of 4 blocks and a vertical base of 3 blocks pointing upward. The 5 that is connecting them is the hypotenuse of the triangle, and that's how I knew it was 5 in the first place. You all already know Pythagorean's theorem, so 4 squared plus 3 squared will equal my hypotenuse squared. This vector is my hypotenuse, and its x and y components are essentially just the legs of the triangle, which is pretty cool. And now I don't need the graph paper at all. I don't need the blocks to count. If I've got a little right triangle set up with my vector, then I am good to go. Now to solve for this angle, to figure out what the angle is in degrees, I can use my right triangle trigonometry. Make sure you are very comfortable with right triangle trigonometry. For any angle theta, the sine of that angle theta is the opposite side of the triangle divided by the hypotenuse. The cosine of theta is the adjacent side divided by the hypotenuse. And the tangent of theta is the opposite side divided by the adjacent. So looking back at my graph, if I've got an angle theta above the x-axis, that means my x component, my 4, is my adjacent side. And my y component of 3 is my opposite side. So I can pick any trig function that's my favorite, since I know all the sides of the triangle right now, and just roll with it. I'm going to go with sine because that's usually my little default. Though a lot of times I go with tangent. I don't think tangent gets enough credit, and it's lonely. So love the tangent. So sine of theta equals my opposite side, that's 3, divided by the hypotenuse. That's 5. All right. I'll take an inverse sine. Theta equals the inverse sine of 3 over 5. And solving that out, I find that I get theta to be, let's see, about 37 degrees or so. Cool. Now, why is this useful? Imagine that I'm not just dealing with triangles, or I'm not just dealing with graph on graph paper for my middle school math class, but instead, I got a projectile motion problem going on. Here's how that might look. Let's say I'm hanging out in the jungle, and all of a sudden, I get attacked by, I'm going to go with a jaguar. And all I can say at this point is, thank goodness I'm not being paid for my artistic abilities. So, this jaguar is attacking me, and I have really quick reactions, and I happen to just kick up at just the right moment and send it flying away from me. And I send it flying with an initial velocity of 7 meters per second at an angle of 20 degrees above the horizontal plane. You can always imagine some horizontal plane right at the object you're referring to. All right? Now, 7 meters per second, that's great, except the only acceleration he's going to feel is due to gravity, and that's straight downward. So, if I wanted to study a bit more about where this jaguar was going to land, let's say I've got a friend with me, and I really prefer if the jaguar didn't fall backwards and just happen to land on top of her. So, I got to make sure that that doesn't happen. Thankfully, I know physics, and I can make that work. The way to do it is to break this vector into its x and y components to begin with. So if I have 7 meters per second at an angle of 20 degrees above the horizontal, I can figure out, okay, cool, it's heading up and to the right, but how fast to the right and how fast up? And to do that, I just complete the triangle. So generally, your original vector will be the hypotenuse of the triangle. And your x and y components will be the legs. And I can find it just by some right triangle trig. So x is adjacent to me, so I've got the cosine of 20 degrees is equal to the adjacent side. I'm going to go ahead and say this vector, I'm going to call it v naught because it's an initial velocity. V with a little subscript 0 is 7 meters per second. I'm going to label my x component v naught x because I'm that creative, my y component v naught y. So the cosine of 20 degrees will be v naught x divided by 7 meters per second, my hypotenuse, adjacent over hypotenuse. So my x component will be 7 meters per second times the cosine of 20 degrees. And I'll let you all solve that out if you'd like to know its numerical value. I'll do the same thing on the y side, except this is opposite the 20 degrees. So I would get my initial y velocity to be 7 meters per second times the sine of 20 degrees. We'll talk more in the next unit, projectile motion, what I can do once I've gotten it broken into its x and y components. But until then, we're just going to stop for here in terms of breaking it down. Now let's say I've got some x and y components that I already know, and I want to figure out what the total vector is from those x and y components. Well, I just use good old Pythagorean theorem. So if I've got an initial velocity in the x direction of some value and in the y direction of some value, and I want to know what the total initial velocity is, I can just say, well, my total initial velocity squared equals v naught x squared plus v naught y squared. And so, in summary, all vectors can be broken into its x, or horizontal, and its y, or vertical, components. If I got vector A, I just travel as far to the right as vector A does without going up at all. That is my x component. The y component of it is how far up it went without traveling left or right at all. I combine that to make a right triangle, where my original vector is the hypotenuse, my x component is the horizontal leg, my y component is the vertical leg. Not too bad. Now if I got a couple of vectors and I need to add them together, there are a few ways to do it. One is just graphically, you can look at them and add them. The one we'll use more often is numerically. Now the quantitative numerical way of doing that is this. You already know that only identical units can be added. No raccoons plus cupcakes. Not only that, only identical components of vectors can be added. So I cannot just straight up add an x component with a y component. I can't add a vector that's going up and to the right with a vector going up and to the left unless I first break them into pure x and y and move from there. So, the way to go about it, find the x and y component of both vectors you're trying to add together. Add the x components from both vectors together. Add the y components from both vectors together. And now you've got what's called the resultant. Anytime you add vectors together, their sum is called the resultant. So take the resultant's vectors x and y components and Pythagorean theorem that mess. I'll go through just one really brief example. If I have vector A, it's pointing up and to the right at an angle of 40 degrees above the x-axis. And I've got vector B, it is pointing up and to the left. And it has, let's say it's above the negative x-axis, so above the left-facing x-axis, 20 degrees. Vector A has a magnitude of 7 meters. Vector B has a magnitude of 3 meters. And I want to find out what A plus B is. Well, first I break them down into their individual x and y components. In the interest of time, I'm going to skip those steps because that's what I just described. Use the angle and use the hypotenuse to form the other legs of your triangle. So once I complete that, I see my x component is 5.36 meters to the right. My y component of vector A is 4.5 meters up. Now for vector B, my x component is 2.81 meters to the left and 1.02 meters up. And I found that just by using trig functions for each vector individually. Go ahead and try it yourself, see if you get the values I get. If not, that might be a good question to come in and ask when we discuss this. Now, I mentioned earlier that a negative for a vector just flips it 180 degrees. Anytime you're dealing with vector problems, imagine again the little grid, the XY grid. Now conventionally, usually on the x direction, rightward is positive, left is negative. In the y direction, up is positive, down is negative. Usually. You can define it however you want, but I like it this way. So therefore, AX is up, AY is up and BY is up. I'll treat those as both positive. AX is to the right, I'll treat that as positive, but BX is to the left. So I'm going to declare that that is negative 2.81 meters. Now I just add the individual components. So for my resultant vector, the x component will just be AX plus BX. So 5.36 plus negative 2.81 comes out to be 2.55, positive 2.55. So that means my resultant vector would have an x component of 2.55 meters to the right, because that's the positive direction. I'll do the same thing in the y direction. My resultant vector in the y will just be the y component of A plus the y component of B. That's 4.5 plus 1.02. That should get me 5.52 meters. Cool. So I've drawn these resultant vectors here. Our x being 2.55 meters to the right, our y being 5.52 meters up. And I just realized I did not do this to scale at all. So I'm sorry about that. Now what is the final answer though? What is the sum of vector A plus vector B? A is 7 meters up and to the right, B is 3 meters up and to the left. Well, now that I've got my resultant vector, I can find the total final resultant with the Pythagorean theorem. I've got its x component, I've got its y component, so vector r is just going to be 2.55 squared plus 5.52 squared, and I'll take the square root of that whole honkin' thing. And it comes out to 6.08 meters. So ladies and gentlemen, that is how 7 plus 3 can turn into 6.08. Fascinating. Now, what's physically happening when I add these two vectors together, if I want to look at the graphical method, if I have vector, again, I've named them A and B. This time vector A is up and to the right. Vector B is also up and to the right, but a little bit less up, a little more horizontal. All you got to do if you want to add things graphically just to see what it looks like is take your first vector, then move your second vector you want to add to it so that the end of vector 1 equals the beginning point of vector 2. You just stack one right after the other.
then a straight line that connects the very beginning of vector 1 to the very end of vector 2, there's your resultant. All right, so please, vectors, super important. You got to know how to break them into x and y components. You got to know how to add them together. So if you have questions, please, please, please come in and ask those questions. Until then, see y'all later.